Alright, so this is part 2 of your block day lesson. Part 1, I showed you how to do sequences and series on your calculator, and we went over homework 2. So now we're going to be focusing on geometric sequences and series, and then look at how we can calculate them based off of some given information. So we're going to jump straight into that. Here we have a sequence of numbers, 2, 20, 200, 2000, and I want you to try and write the next three terms in the sequence, and then I want you to try and write an explicit formula for that sequence. So take a moment and do that, and then look at how I am doing it. So pause it now and try that. Alright. Well, notice each time we're increasing by a power of 10. 2 times 10 is 20. 20 times 10 is 200. 200 times 10 is 2,000. 2,000 times 10 is 20,000. 20,000 times 10 is 200,000. And 200,000 times 10 is 2 million. And so we have our sequence here. We're increasing by a power of 10 each time. So if you think about that, we're multiplying by 10 a bunch of times. Anytime you multiply by 10 a bunch of times, it's the same as taking your 10 and raising it to a power. So each time, this is going to represent how we're getting from a term to the next. 10 to the power of n. And now let's think about what that would mean. If a sub 1 is our first term and we plugged in 1, then we'd have 10 to the power of 1 is 10. And that can't be right because our first term is 2, and we haven't yet multiplied by a power of 10. And so we're going to say 10 to the n minus 1, kind of like our arithmetic sequence. We hadn't yet added our common difference, and so we had that multiple as n minus 1. Well, it's the same idea here, except now it's an exponent. So now what would happen if we plugged in n? Well, if n was 1, we'd get 1 minus 1 is 0. 10 to the 0 is 1, but we need that first term to be 2, and so we're going to multiply by 2. And this is our explicit formula here for this geometric sequence. This is a geometric sequence because to get from one term to the next, you are multiplying by a common ratio r. And so, how do we figure out what that common ratio is? Well, this one you can just look at it, but it's the same idea as how you do it for a arithmetic series to find the common difference. Take a term, value, 200, divide that by the value of the previous term, 20, to get your common ratio r, which is 10. Now, for the common difference, we subtracted. For the common ratio, we are dividing. Ratio means rational number. It is talking about a fraction. So pick a term, divide the previous term to find your ratio r. Where did that 2 come from? Well, the 2 is our first term. So if we generalize this to a sub n, our explicit formula for a geometric sequence, we get a sub n equals our first term, a sub 1, times our common ratio r, raised to the power of n minus 1. So this will always allow us to generate a geometric sequence. A sub 1 first term times the common ratio r, raised to the power of n minus 1. So let's try that with this problem right here. Write the explicit formula for the following sequence. Well, that should be pretty quick. A sub n equals my first term, which is 8, times my common ratio, which I can find by choosing a term and dividing the previous term. So 2 divided by 4 is 1/2, so my common ratio is 1/2, which you should remember multiplying by 1/2 is the same as dividing by 2. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1, etc., etc., etc. I'm going to need to raise my ratio to the power of n minus 1. And just like that, I have my explicit formula for this geometric sequence. But the next logical question is, how can we find the sum of a geometric series, just like we found the sum of an arithmetic series? Well, it's not actually going to be quite as easy. But I'm going to show you how we can come up with a formula to do so. Let's start with this notation here. Notice we have a sigma notation. Notice that this is just the explicit formula of a geometric sequence. I'm using i's here instead of n's because we want to go up to the nth term. But think about what would happen. If I plugged 1 in for I, I'd get my first term. If I plugged 2 in, I'd get my second term. If I plugged 3 in, I'd get my third term. If I plugged n in, I'd get my nth term, which should be in the form of n minus 1. So this works, and what we're saying is this is equal to S sub n, the nth partial sum of this series. So we're going to focus not so much on the sigma notation, but we're going to focus on this side and this side over here. That's going to be the moneymaker. So the first thing we're going to do is we're going to multiply both sides of this expression by 1 minus r. And if we do so, on the left we'll just have S sub n times 1 minus r, and on the right we'll have that whole mass times 1 minus r. And the logical thing to do then next is to distribute this 1 minus r in to all of these actual terms. And so we're going to do that. We're going to leave it on the left, but we're going to distribute in on the right. And so if we do that, think about what we're doing. We're going to be taking 1 and we're going to multiply it by the first term. Well, that's just going to give us our first term, a sub 1. But then we're going to take the r, or rather the negative r, and multiply that by the same term, kind of like foiling in that 1 minus r. So if I multiply a sub 1 by negative r, I'm going to get a minus a sub 1 times r. And then I'm going to do this to my second term. I'm going to multiply it by 1, and that's just going to give me my a sub 1 r, the same thing that was there, right? Each time I'm starting by getting the same thing that is there. But then afterwards I'm multiplying by that minus r, which is going to change this from being addition, a positive a sub 1r, to a negative a sub 1r, but I'm multiplying by r, which means I'm increasing the power on the exponent. So from an exponent of 1, I now have an exponent of 2. And then I'm going to do the same thing with my next term right there. I'm going to multiply in that 1, which is just going to give me the term again, so a sub 1 times r squared. And then I'm going to multiply in by that negative r, which is going to change the sign and increase the exponent by 1. And I'm going to continue on in this manner all the way up until I hit that last term right there. So I'll multiply my 1, which will give me the last term. So a sub 1 times r to the n minus 1. And then I'm going to multiply by the negative r, which is going to change the sign and increase the power by 1. So if I have r to the n minus 1 and I'm increasing that exponent by 1, I now have a sub 1 times r to the power of n. And notice what's happening here. In each instance, I have a bunch of terms that can cancel. My a sub 1 times r will cancel with that negative a sub 1 times r, so those are gone. And then my next term, my negative a sub 1 r squared, will cancel with my positive a sub 1 r squared. So that's gone. And if I had listed a fourth term here, I would end up with an positive a sub 1 r cubed, so that would be gone. And if I had listed the n minus first term there, I'd get a negative a sub 1 r to the n minus 1, so that would be gone. And so the only thing that will remain is that first term a sub 1 and that last term negative a sub 1 times r to the power of n. So that's the only thing that is left. And so, canceling all that out and simplifying it, we end up with this. On the left, we still have our s sub n times 1 minus r. On the right, we have a sub 1 minus a sub 1 times r to the n. So kind of a similar idea to the arithmetic sequence, and series rather, in that we have a first term and a last term. Now, we want s sub n, so we need to solve for s sub n by dividing by 1 minus r. And when we do so, we end up with this formula right here. A sub 1 minus a sub 1 times r to the n divided by 1 minus r. But notice in the numerator, both of those terms have an a sub 1, so we can pull it out to get our final expression here. A sub 1 times 1 minus r to the n over 1 minus r. And that is our summation formula for the nth partial sum. S sub n equals a sub 1, the first term, times 1 minus our common ratio raised to the number of terms divided by 1 minus our common ratio r. So now let's just look at a couple problems where we can use this, and then we'll call it a day. So we want to find the explicit form of this equation, and then we want to calculate the sum of its series. So explicit form is just going to be first term 2 times our common ratio, which you can look at this and identify as 2 raised to the power of n minus 1. And now we want to calculate the sum of this, so we need to figure out how many terms we have there. Well, if you count those terms up, we have 12 terms there. And so our 12th sum is going to equal our first term, which is 2, times 1 minus our ratio, which is 2, to the power of 12. And we're going to divide that by 1 minus our ratio. And we can calculate this to find the sum is 8,190. Now, if you're typing this on your calculator, I would type it as 2, I'd open a parentheses, 1 minus 2 caret 12, close your parentheses. If you're on an old one, if you're on a new one, it gives you the exponent and then it's all nice. But then divided by 1 minus 2, like that. And then you'll get your 8190. You should also check your sigma notation or try the summation of the sequence and see if you can get the same value that way. You absolutely should. So the next problem is here, and it seems like probably won't be so hard based off of that last one, but it actually gets kind of tricky. So let's start this using what we know so far. I want to find my common ratio. So you can probably look at this and see that it's 5/3, but again, if it was something less obvious, you could say pick a term like 5/3 and divide it by the previous term 5, and what happens? Well, if you don't like how that fraction looks, think of it as 5/3 dividing by 5 is the same as multiplying by the reciprocal of 5. So you can write it as 1/5, and then you can see the 5's cancel, and you're left with 1/3. In the same way, I like to do that and say, okay, well now I have 1/3. However you look at it, a ratio, R, is 1/3. And so we can write this explicit formula. A sub n equals my first term, 5, times my common ratio, which is 1/3, raised to the power of n minus 1. And we have that classic problem of we don't know what number term this is right here. And so we could set up an equation. We could say that 5 over 729, the value of the nth term, equals 5 times 1/3 raised to the n minus 1, and we want to solve for n. Well, before we start thinking about how we're going to do that, why don't we simplify this equation a little bit. Both of those sides have a power of 5, and so we can divide by 5 on both sides to simplify it to 1 over 729 equals 1/3 to the power of n minus 1. Notice what we have here. We have an exponential problem here with an unknown value stuck in the numerator. How do you get an unknown value out of the numerator? Well, you use logs. And so anytime you're trying to do logs, you need to first get rid of that coefficient, that 5 in front of the 1/3. You need to get rid of that before you can then go on and actually use logs on this exponential bit. Now, do you remember how to use logs? I hope so, but chances are you need a refresher. So remember that the log base A of C equals B if and only if A to the power of B equals C. These two forms are equivalent. You can go back and forth between them, and we're going to do that here. Notice that the base of the log is the same as the base of the exponent. That's where I always start. And so if I'm writing this log, I know that the base of this log is the same as the base of the exponent, so my base is 1/3. And then notice inside the log is the thing that the exponent is equal to, that 1 over 729. So that is inside our log, 1 divided by 729. And that equals what that original exponent was. So our original exponent was n minus 1. So now, notice our goal has been accomplished. We got the n minus 1 out of that exponent, which means we can solve for n. Now, if you don't remember how to get into that form from exponential form, well, maybe you remember the plog rule. And so just take the log of both sides. The log of 1 over 729 equals the log of 1/3 to the power of n minus 1, like that right there. And plog rule says you can take that exponent and move it down in front. So really what we have is the log of 1 divided by 729 equals that exponent, n minus 1, times the log of 1/3. And what do you do at this point? Well, divide by the log of 1/3. And so we have the log of 1 divided by 729 divided by the log of 1/3 equals n minus 1. And that right there, my friends, is the exact same thing we came up with in the purple equation, but it is using change of base formula. Change of base formula says take the log of the argument, which is the log of the thing in the parentheses, and divide it by the log of the base. The base stays in the basement. So they're equivalent. We got there in the same way. If you went the purple method and then needed to calculate this on a TI-83, then you would actually have to use change of base formula to calculate it. And you have to calculate it like that. If you're on a newer operating system, go ahead and hit that alpha window again to get the new options. You'll see there's a log base option there, which will allow you to actually enter the base of 1/3, and then you can calculate this right away. Either way, however you do it, plug that in your calculator, and you should find that n minus 1 equals 6, which means that n equals 7. A lot of you are going to be like, oh, n is 6, and you're going to stop, and then you're going to be sad, because that is absolutely not correct. Don't forget to add that 1. N is 7. Now, a bunch of other of you are going to say, well, I need to figure out what number this is, so I'm going to take 729, and I'm going to cube root it, because we're dividing by 3 each time. That absolutely will not work. That is not mathematically valid. Please don't make that mistake. You have to use logs to get this, or if you're clever, you could come up with some other way to get from there to there, but I'll let you worry about that. I'm going to use logs because it's good use, it's good practice of what we have done already. But what was our goal? What was the whole point of this? Well, we know that this is the 7th term. N is 7. And we want to find the sum, so we need to use our summation formula, which is going to say the sum of the 7 terms will equal the first term, a sub 1, which in our case is 5, times the expression 1 minus our common ratio, which is 1/3, raised to the power of n, which is 7, divided by 1 minus our common ratio, 1/3. If you're typing this into your calculator, I would type it like this. I would say 5 parentheses, this is my numerator now, 1 minus, I do a parentheses, 1 divided by 3, close that parentheses, caret, exponent 7, close that parentheses. Always match up your parentheses, one set of parentheses around the 1/3, one set of parentheses around the numerator, divided by the denominator, open parentheses, 1 minus 1 divided by 3, right there. Close your parentheses, call that good. Find your answer. You should get the fraction 5,465 over 729, which is roughly the same as 7.497. Now, you might have gotten very close to that number, 7.497, if you did your little cube root thingy, but that is a coincidence because we're adding really small things together. Please do not think you did the problem correct just because you got a number really, really close to the actual number. This is the exact value right there, that fraction, 5,465, and we got there using logs. So, that is our lesson for today. Oh, wait. So let's go ahead and do this last problem real quick. We're going to do the same thing. Let's write our explicit formula. A sub n equals our first term, 20, times our common ratio, which is, what is our common ratio? Well, pick a term, -10, divide it by the previous term, 20, get your ratio of -1/2 right there. So our ratio is -1/2 raised to the power of n minus 1. And we could do the same thing. We could say that last term, -5 over 32, equals our first term, 20, times our common ratio, -1/2 raised to the power of n minus 1. And we could solve all of this using logs. But here's the problem. We would end up with negative values inside of our logs, which are not going to get us where we want to go. Cannot calculate the log of a negative number, at least not with real numbers, and so that is an issue. But think about the actual numbers here, not whether they're positive or negative. Think about just those numbers. Our goal is just to figure out what number is this. That number is not affected by whether or not it's positive or negative. That's merely the coefficient out in front. So if you think of just these purple numbers as the sequence, it would be the same sequence. It would be 20, except instead of a negative r, it would be just a positive r, 1/2 to the n minus 1. And so that last term, let's think of that as a positive 5 over 32. Let's think of that 1/2 as a positive 1/2, because this way I don't have to worry about any negative log stuff, but it's still going to get me the correct term number. So first thing I need to do is divide by 20, and so I'll get 5 divided by 640 equals 1/2 to the power of n minus 1. And now I can go ahead and rewrite this in log form. The log of, same base as the exponent, 1/2, of the, whatever the exponent expression is equal to, 5 over 640, will equal n minus 1. And then we need to solve for n. So again, if you're on an old calculator, you gotta say the log of 5 over 640 equals the log, or sorry, divided by the log of 1/2. If you're on a new one, just hit alpha window and do a log base. Well, this will equal n minus 1, and you should get 7 for that, which means n equals 8. So this is our 8th term right there. Now, if you don't believe me about that whole just pretending it's positive thing, go ahead and use your calculator to generate that sequence with a positive 1/2. You'll see that you get the same sequence here, except just everything's positive. If you make the 1/2 negative, you get the sequence with the alternating positive and negatives. So it is absolutely 100% valid. You can absolutely do it that way. And it just avoids having to figure out how to deal with negative log stuff, which wouldn't be fun. And so now we go back to the original problem, which is calculating this sum. And so the sum of the 8 terms is going to equal the value of the first term, 20, times 1 minus our ratio. Our ratio is negative 1/2. At this stage of the game, the negative absolutely does matter because we need that alternating positive negative bit. Notice I am putting the negative 1/2 in parentheses. You absolutely need to do so. You absolutely cannot simplify that down to 1 plus 1/2 to the 8th. Well, in this instance you could, but if it was an odd exponent, you could not. Or even exponent, you could not. Actually, I'm being silly. You couldn't do that. You couldn't do that. So be safe, put it in parentheses. And then 1 minus our ratio, which again is negative 1/2. There you have it. Calculate that sum in your calculator. I would type this as 20 parentheses for the numerator, 1 minus parentheses negative 1/2, close the parentheses, caret 8, close the numerator, divided by parentheses 1 minus parentheses negative 1/2, close your fraction, close your denominator, type that in, and you'll have your answer. And your answer should be 13.28125, which is equivalent to 425 divided by 32. And I would recommend you try this. Well, first off, we're supposed to write in sigma notation as well. So sigma of n1 up to the 8th term of our expression, 20 times negative 1/2 to the power of n minus 1. It equals that. It equals the 8th partial sum. But I would challenge you to do this on your calculator as well and make sure you do actually get that number. Now that is the last problem we're going to do together. This is your homework problem for tonight. You're interviewing for a job and you receive 2 different offers. Which offer is going to be best if your goal is to be making as much as possible after 5 years? Which is the best offer if your goal is to make as much money over the total 5-year contract? Now, a couple pieces to note here. 6%. If you're writing 6% as a decimal, that is 0.06. It's not 0.6. 0.06 is 6%. But here's the issue. We need to write this as a geometric sequence. But to do so, you need to figure out what your common ratio r is. and it is not 0.06. If your common ratio R were 0.06, that would be saying the second year you work, you're only going to have 6% of your previous salary. But you don't want 6% of your previous salary, you want 106% of your previous salary. You're increasing by 6%, which means you have that original 100%, and you have an additional 6% on top, which means if we want this fraction to be accurate, we need 1.06 to give us that 106%, representing a 6% increase, not 6% of what we had the year before. So think about that. And the second thing you need to think about is these two questions right here are asking two very different things. The first question, which offer is best if your goal is to be making as much money as possible after 5 years? That question is essentially asking you which offer will give you the highest yearly salary on the 6th year. Because if you've been working for 5 years, on the 6th year you will be making blank amount of money. The second question, which is best if your goal is to make as much money as possible over the contract, 5 years, that's saying over those 5 years of working, which of these two options will give you the largest total amount of money. So, first question, asking for the term of the sequence. Second question, asking for the summation of the sequence, the series. There you have it. Give it a shot. We'll go over it in the next video.